Okie dokie. So now we're going to move on to the process of designing, fabricating, integrating, and launching spacecraft. So here is the verification and validation model. There are independent procedures that are used together for checking a product, service, or system so that it meets requirements and specifications and that it fulfills its intended purposes. Verification is the act of proving that the system meets all of its specified requirements, and validation is the act of ensuring the end product stakeholders' true needs and expectations are met. I want you to make sure you know the difference between verification and validation. Validation is more purpose, and verification is more function. In this class, we are going to mostly do the definition and design part of the process, but I do want you to be knowledgeable of what comes afterwards in the design process, the verification and validation part, because there are direct links between, say, stakeholder analysis and the final mission operations. They're inversely related to each other. So what you do in, say, Tradespace is going to directly affect the component expectations that you're looking for in component performance analysis. Another thing to say is that every single one of these phases in the design process has some kind of review that you need to pass to move on to the next phase. These reviews are like quality control checkpoints to make sure that your design is sufficient enough to move on to the next phase. All of these phases should have a certain schedule associated with them so that you're not overrunning your schedule. Okay, so let's go over the different phases. The first phase is a stakeholder analysis. A stakeholder is a member of groups. Without those support, the organization would cease to exist. So some examples for NASA, the different stakeholders are US taxpayers, Congress, and the community of scientists and engineers who contributed to the decadal surveys and strategic plans. So you'll see sometimes that Congress writes in different NASA missions into bills, which obligates NASA to pursue those missions. Also, US taxpayers, I mean, we're funding them, we're funding NASA, so we have a say as to what kind of missions or programs happen at NASA. For businesses, a stakeholder could be customers or clients, it could also be investors. For the defense side of space, like Space Force or the National Reconnaissance Organization, they have very similar stakeholders to NASA, as it's a government agency, such as the US taxpayers and Congress. But I think the intellectuals that are driving this organization differs from NASA in that instead of scientists and engineers, we have military strategists who can also be scientists and engineers, but have a more military interest in mind. Okay, in this class, the stakeholders are going to be NASA, myself, your instructor, and each other. These are the people who set up expectations for the mission performance. So I asked you all to read NASA's Decadal Survey, Strategic Plan, and Small Sat Technology. That was because I want those priorities to significantly inform the type of mission that you're going to carry out. You want to be able to do something that NASA feels is worth funding, especially if we're going to apply for the NASA's DSLI. So these stakeholders are the people who are going to set up expectations for the mission performance. So you were tasked to think of 5 mission ideas each. Within the coming days, your group must decide cohesively which mission idea to pursue for the rest of the semester. These factors will be NASA's interest, feasibility in forming a cohesive design in a semester, and cost. And your requirements from the assignment were the proposed science or technology demonstration could be implemented with a payload that fits within a 1U, which is a 10 centimeter edge length cube, and that the science mission, or it doesn't have to be science, it could also be technology, shall orbit around the Earth or Moon. I'll talk a little bit about the Artemis CubeSat kit project as a motivating example. So the stakeholders for this project that I got funded, NASA was the funding agency with these other groups that were interested in funding. They give a little bit to the pot of money. The Space Grant Consortium and the Office of STEM Engagement focus on education, which is good because we talked about undergraduate education. The chief economist was interested in seeing all of these different states launch a CubeSat. The green states are those that haven't launched a CubeSat before, so we wanted to specifically target those states, and the light red states that have been selected but haven't flown yet either. And also the Space Technology Mission Directorate had interest because they wanted to have a technology platform that was streamlined, that you could easily add payloads to and just send it into space for a tech demo or space heritage. We also have undergraduate students who are our clients. So you all are a stakeholder in this project. We were also targeting academic institutions without an aerospace program who could potentially buy these kits for classroom instruction. And I already talked about the states, and we're distributing these kits to the other community colleges because we wanted to make this aerospace program as accessible as possible. For system and mission requirements definition, this is the next phase after the stakeholder analysis. So once you have a concept locked in, you should be able to form high-level requirements. These requirements dictate how the system functions and the scope of the mission performance. This requirements definition acts as the interface between the stakeholders and the development team. So there's a little bit of formalization of here are our wants and desires. How do we articulate that in a way that describes the mission? The people who come up with the system and mission requirements are the chief scientists, the chief engineers, and the program managers. And those three are commonly the trio of power in a program or a mission. They are constantly negotiating with each other for their own interests. So the chief scientist is most interested about the payload being represented. The chief engineer is most interested in the engineers having a feasible design. And the program manager is most interested about cost and schedule. So you can see how some of those can be at odds with each other at times. So these leaders need to constantly be in tension to make sure that there's compromise happening. And I was asked, how much detail does the PI provide at the start? So this differs from program to program. I think that teams are composed of unique people, snowflakes, who they all work in different ways. So I can give you examples about, even for our small satellite programs at HSFL, Dr. Englert, for example, is a very hands-off PI. And then Dr. Wright, who is the PI for the high time mission, is more involved. I think that, you know, there are benefits to each kind of involvement, but having a chief scientist, if you don't have a PI, involved as the chief scientist, then having someone who's a stakeholder in the science getting done as a part of the development process is important for having, that pillar of interest represented throughout the whole design process. The system and mission requirements definition is validated by the system requirements review. Reviews have expectations and evaluation criteria the team must meet. So we will do abbreviated versions of the reviews. The system requirements review will just kind of glaze over. The reviews later on this semester that I really care about are the preliminary design review and critical design review that we'll talk to you in a little bit in later phases. The Artemis CubeSat kit, its system requirements were, and you'll note here the use of the word shall. So good requirements that have words really matter when it comes to requirements. Shall is a very strong word. It's firm. It's saying it will happen. There are other words that you can use that are softer. So shall is a very hard word. I think in the systems engineering handbook, I don't want to get it wrong, but there are other words for softer constraints. So the Artemis CubeSat kit shall be rated for spaceflight operations, shall be low cost and accessible to universities and private individuals, shall function as a basic spacecraft with a payload in space, shall at least include components in educational ground kits, extended to spaceflight equivalents, shall include software that is intuitive for undergraduate students, shall be accompanied with this online course and tutorials for spacecraft mission design, and shall be tested to meet environmental requirements set forth in the NASA GEVs for spaceflight. You'll notice NASA GEVs, this is, I don't remember what G stands for, but Environmental Verification System? Anyway, NASA GEVs, commonly referenced because these are environmental requirements that are ubiquitous for things that we send to space. It includes things like outgassing, and then we have other external documents that we will have to adhere to for this CubeSat, like a NanoRacks, which is a launch provider requirement document, and a CubeSat standard document that we also have to adhere to. So requirements, they come from these external documents, but they also come from the stakeholders, like we were talking about. Yeah, we will talk about requirements very in depth because they're very important for the engineering process. Okay, the next phase is the system architecture or subsystem performance decomposition. So we're just talking about system and mission requirements. From those, your team should be able to define a system architecture and decompose the system requirements into subsystem requirements. So you have a system, which is your entire spacecraft. You then can assign functionality or performance into the distinct subsystems. Some of the system requirements can touch multiple subsystems. Some are only relevant or directly relevant to one subsystem. Some subsystems affect other subsystems. So you need to think about all of these different relationships when coming up with requirements. These requirements are defined by the development team. So again, we have our leadership triad, the chief scientist, engineer, and program manager. Actually, the program manager, maybe not so much, but definitely our new characters are the subsystem leads. These subsystem leads are responsible for making sure that their subsystem is represented, that they are getting enough money for their components, that they are meeting the subsystem requirements that are agreed upon in this phase. They are the technical experts that represent their team that works for them, but also they're conveying the technical expertise on to the chief engineer or the larger systems engineer. This phase is verified by other scientists and engineers outside the development team. So you think the end deliverables for this phase are a system architecture and subsystem requirements. For our class, we're going to have each of the teams review the other team and vice versa. So we'll have a PDR in which you're presenting your system architecture and subsystem requirements and also a preliminary design. During these reviews, we're supposed to catch any kind of feasibility issues, any technical mistakes or concepts that aren't really well thought out yet. Yeah, so questions and clarifications are very encouraged during this phase of the project. Okay, the preliminary design review, a sneak peek into something you'll do later on in the semester. You should be able to offer a preliminary design of the spacecraft and give good support for why you picked these presented solutions. Note that the solutions may not be in the final design, but the criteria for choosing the solutions must be rock solid and well thought out. So this is the criteria. I just want to stress that even though your solutions may not be in the final design, you're offering some initial starting point for the design. You need to make sure that you have a solid idea of how you're evaluating the design. You're drawing subsystem requirements and system requirements that have function and performance associated with it. So those are good criteria for making sure that your initial design holds up to it. So yeah, this is like the initial state. When we go to critical design, we're reiterating the design. So you'll sift through, you'll like move one piece of the puzzle in the solution, and then that could affect other components. So you'll keep iterating and iterating, and that's why your preliminary solution may not end up in the final design. Another thing in this design review is that the components in the interfaces do not need to be detailed. You can have components initially selected from a vendor, and you may not know exactly how they are put together. And that's another reason why things may not end up in the final design, because you could find out that your component is not compatible with another component, or like the interface is not supported. So that's why we have criteria fleshed out, but maybe components not so much. All right, the Artemis CubeSat kit overview. Here is it's past preliminary design review. It's probably critical design review, but I wanted to show you just general inclusion of components. So we have a CubeSat kit. The anatomy is being taken or decomposed in this exploded view. We have the structure that's framed, and then we have these solar cells that are going on the outside with the wall panels. And then each of these boards represents a different subsystem. The basic payload that we give with all of these kits is a Raspberry Pi camera. There's an antenna there, and there's a radio within this PiCube board. There are batteries for power. There's also a power distribution board and an onboard computer. There are also heaters that will go on top of the batteries that are not labeled. The Artemis example subsystem decomposition. So let's take one of the system requirements from the Artemis kit. The CubeSat kit shall function as a basic spacecraft with a payload in space. To decompose it, we have additional requirements that breaks it down. So say for the power system, The CubeSat shall generate power in LEO and provide sufficient power to all other bus components. The CubeSat thermal system shall verify or regulate that all components are within acceptable thermally operational range. The CubeSat ADCS system shall estimate its position to within 100 meters and attitude to within 3 degrees. The CubeSat command and data handling system shall store, process, and route all data for the predefined kit components. The CubeSat communications system shall transmit telemetry from LEO. So note here that there is no requirement for commanding. And the CubeSat structure shall be contained within 1U and offer flexibility in mounting components internally. These requirements are a little bit mushy compared to the requirements that I want you all to come up with. The reason why these are mushy is because we're trying to offer as much flexibility to our end users as much as possible. What I really want to see to the level of detail is something like this. The ADCS system shall estimate its position. So here's verb, noun, and then numbers with units. Like you want to have an evaluation metric with a number, some threshold, and units associated with it. The next phase, Tradespace exploration and design solution. Subsystem requirements need solutions. To get a solution, you will investigate multiple technologies or potential solutions that must be considered with definitive evaluation criteria. So that's what I was just talking about. The evaluation criteria must be explicit. You use those evaluation criteria to drive the searches for potential solutions. At the critical design review, which will be the culmination of this semester's work, you should be able to offer your best, well-researched design of the spacecraft and give good support for why you think this solution will achieve the system function. This time around, the solutions must be rock solid and well thought out. The components and interfaces need to be detailed, and the analyses and preliminary testing must be presented. At this point of the design, you're trying to prove that you have thought about this well enough that you can start building it. And ideally, when you buy and build, that everything should hook up correctly. The first pass should theoretically work. In reality, the CDR is your best effort in having, smooth sailing for fabrication and integration, but there are going to be little things in the fabrication and integration process that makes you change the design a little bit, but it shouldn't change the design drastically. They're just little tweaks so that you can stitch theory to reality. So here I wanted to show you interfaces between the different subsystems. You'll see that there are different voltage levels defined for, say, the payload and for the onboard computer that are given by the electrical power system. There are different communication interfaces that are labeled, like the camera has a specific CSI interface. The temperature sensor has SPI, the PyQ communicates through I2C and UART. So all of those I'm expecting to see in the CDR at least. Other stuff that you could present during the CDR, for the Artemis CubeSat kit, we did power analysis, so power budgeting. We did a structural analysis. We also did a link budget analysis and thermal analysis. So these are all things that I would expect to see in the final critical design review. Okay, so we are not going to get to component development for your particular mission this semester, but next semester, that is in the plan. But I want you to be aware of what the future is like so it informs your design process. Component development. For the components that need development, like custom boards or mounting brackets, initiate the development process. Start buying components. The critical design review just gave you the green light to fabricate this design. So at this point, you have dedicated funds to a design. And then I've kind of smushed the rest of the process because it's kind of like the same process, but at different levels. So we're going to move up from the design, from the components to subsystem to system, and then to finally delivering your spacecraft. So for your component performance analysis, you need to prove a level of component performance that your design solution meets expectations. The same goes for the subsystem, but you need to integrate the components into a subsystem, and then at that level, create success criteria and prove that your subsystem meets the requirements. And then you integrate the subsystems into a system, and you prove that the entire system meets the system requirements that you defined, remember, in the second phase of this project. There's a lot of testing in these phases. Each of these phases is preempted and closed with a test readiness review, at the level of which the last TRR is the flight readiness review. And I think that answered one of the questions that I got. Oh no. So I want to show you one of the tests that we did for component analysis. It was an antenna deploy test. Well, shoot. Okay. Anyway, we had this 3D printed structure with a prototype of an antenna deployment system. We had a power supply hooked up, and after the power supply delivered enough current, there was a wire that burned, burn wire, and then the antenna deployed. So that is one of the tests that you could do during, say, a component performance analysis. Let's see. And then other tests that you can do, for example, are vibration testing. So you'll see this in some external requirements. It comes from the launch environment. When you're on a rocket, you're going to feel a lot of vibration. So you want to prove that all of your components are going to survive on the rocket and function after it experiences that kind of environment. So we have specific test beds, like this vibration table, that imposes that kind of condition on the spacecraft. And then you can test it on ground. We also have thermal vacuum chambers, where you're looking to see that the batteries survive this. What that means is it's going to experience certain thermal conditions, certain vacuum conditions, and you want to make sure that it can still store and recharge in this condition. Okay. Finally, the moment we've all been waiting for, once the system is delivered and launched, it's up to you to communicate with your spacecraft and see that the spacecraft performs its mission in space. This phase incorporates a lot of different events, like the launch segment or the rocket, getting your spacecraft to its orbit, the spacecraft powering up, deploying, and initiating communications, and the ground segment receiving data and transmitting commands to the spacecraft. This is where the whole project comes to a head, where the original stakeholders that funded your project, they're watching for your success based off of the success criteria that we all set together at the very beginning. Okay, as a reminder, we will only perform the definition and design part of the process, the more fun and ideas-oriented part. Hopefully next semester during senior design, you can finish the rest of the process. The component development portion is hopefully minimized for y'all since we designed, fabricated, and tested most of the rest of your satellite, the Artemis CubeSat kit. Excuse me. Then the rest is on you to analyze and test an integrated spacecraft to deliver an end product. I wanted to go through all these phases with you to remind you of how your work upstream affects work downstream. You need to design systems that are amenable to fabrication or testing that occurs later in the process. Maybe think about how your mission will be operated and build in simplicity into your concept of operations. Your design isn't just about the technical functionality or science, it's also about the process that you have to go through. There's a funny practice to bring in engineers and you want them to be aware of this process. You don't want to throw them into the most fun part, which is the design and the ideas part. Sometimes you want to throw them in the testing part of the process to understand like the bad things that can happen from a bad design phase. This end of the process is like the receiving end of kind of mistakes that are happening up here. It's kind of like the belief that everyone should work in retail to understand like how badly you're treated when customers are mad at you. That makes you a better customer. So same idea there.